Hi all, Dr. Clark here again for Natural Resources. We are going to examine nuclear power. Okay? And so nuclear is kind of one of those polar energies. Okay? You either hate it or you hate the idea of it or you love it and you love the idea of it. There's very few people right in the middle that have no opinion on nuclear power. Okay, so we're going to look at kind of the benefits of nuclear power and the costs. And at first, we're going to look at what does it mean to develop, or what does it mean to have nuclear power. So here is a map of the world, and you can see that there are regions where we say that they're nuclear free areas, meaning that there's been a ban put on it. So here in Tasmania, there's a ban. Okay, no commercial reactors is in gray. So all of Australia, there's no commercial reactors. Most of Africa, a good portion of South America, there's no reactors. All pink or red on the map is going to be decommissioned. So the plants are decommissioned, like Italy and other parts of the world. They're decommissioning all plants. Light blue is considered for decommissioning. Okay, so a lot of Europe is going to have decommissioned plants in the near future. Blue is stable, so no new plants, no decommissioned plants. There's very few parts of the world in the stable portion. Okay, kind of yellow here is considering new plants. Okay, so pieces of Africa, like South Africa, Canada, Mexico. Okay, considered the first plant. Africa again. Okay, Indonesia, some places along there. Building new plants would be green, so the United States, parts of South America, okay, lots of Europe, India, China, and first plant. Other parts in the world have some first plants. Okay, so it's a mixed bag for sure. You got some parts of the world that have none and will not have any. You have other parts of the world that are thinking about building more, and you have some parts of the world getting rid of what they got. Okay, so let's look at nuclear. So nuclear power is not like fossil fuel in the sense that it didn't come from fossils. It comes from native elements. Okay? But nuclear power is not renewable, okay, because you're destructing uranium in this case. Okay, you could also do it with petroleum or with uh, plutonium, protonium. Um, you can also run a nuclear power plant off of that, but there's very limited elements that you can utilize to run nuclear power. Uranium is the most often used. It's not renewable, and it is mined in order to get it. As of 2016, so a couple years ago, there are about 450 nuclear power reactors worldwide and 60 power reactors in construction in 16 different countries. So probably by now, not all these nuclear powers that were in power plants that were under construction have came to fruition, but probably some of them have. So we're probably, you know, 470, somewhere in that range, maybe even 480 in the world today. Now, a couple reasons why I don't have real good numbers on nuclear power plants is a lot of countries will not publish where their nuclear power reactors are or nuclear power plants are for fear of terrorism events, these kind of things. So, you know, a lot of countries will tell you that they have them, but they also don't tell you how many or what's the stage of the uh, reactor, so they don't have to present that kind of information. There are about 158 nuclear power plants that are being planned, and they occur mainly in Asian countries, um, China, India, Japan, South Korea are the ones that have probably the most are furthest along in their plans, and most of these plants are going to be constructed in these regions. You can see the number of reactors, so roughly 450 reactors. The United States have the majority of them. Not quite double everywhere else, but like I said before, France is starting to decommission a lot of theirs. Um, Japan, China, these places are starting to up the number that they have. And so, for the most part, though, the United States leads the way with the number of reactors um, in use currently, and also the number of reactors that are going to be decommissioned. And we'll come back to that. So if we look at nuclear power plants in North America, there's a few west of the Mississippi, but not very many. So Washington, California has a couple, Arizona has a few, Texas, Nebraska, Kansas. The rest of the nuclear power reactors are all eastern part of the United States, a couple in Canada, but for the most part, majority of it comes in eastern United States. Okay, a couple in Mexico. So how does it work? Okay, so now I'm going to spend some time about like how do we get energy from nuclear energy? Okay? And if you remember back when I talked about chemistry, I talked about the nucleus of a chemical being protons and neutrons. Okay? And then that proton neutron is surrounded by electrons. Well, anytime you change the number of protons in a nucleus, you're going to actually change the element. Okay? So if you change the number of protons, you change it to a different element. But you can change the number of neutrons. Okay? And this creates what we call an isotope. Okay? And most elements have different isotopic ratios, so a different number of neutrons inside the nuclei. Okay? That's associated with the proton. Okay? Now, some isotopes are what we call radioactive, meaning that they're not stable. Okay? And they spontaneously decompose. Okay? They break down. These are the isotopes. These are the elements that we're most interested in when we're talking about nuclear energy. So when a isotope decomposes, it's going to release neutrons, electrons, protons, okay? And that release of energy can be utilized by us, okay? So we can basically break down atoms to release energy, okay? And that's what nuclear energy is all about. Same premise with nuclear bombs, breaking atoms to release energy, massive amounts of energy in a given amount of time. Now, some things decompose at different rates. So you have different elements, they have different what we call radioactive half-lives, or the time it takes for half of the material to be decomposed. Okay? So the one that we often use when it comes to nuclear power plants is uranium-235. Okay? Its half-life is 700 million years. Okay, so that takes about 700 million years to go from 1 gram to half a gram, okay, of uranium-235. Plutonium okay, is what we make nuclear weapons out of, typically. Okay? It's about a 24,000 year half-life, and some nuclear plants are fueled off of plutonium. Okay? The rest of these are just other isotopes that we use in many different functions. Okay? Most of you have heard of carbon-14 and carbon-14 dating. Okay? Its half-life is 5,730 years. Okay? Now, remember that it takes that many years to decrease it in half, however much you had. Okay? The importance here, and we can talk about isotope dating, the importance here is carbon-14's useful for dating things that are fairly modern. So things that humans might have experienced. Okay? So let's say we find a cave in Colorado, and inside that cave we find a carcass of a Native American with some clothing and things like that. We can radioisotope date the carbon-14 in that material to establish a date. Okay, the date at which that organism died. And whether that be human, whether that be like a dog, a plant that might be there in the cave, whatever it might be. Okay? Now, that gives us kind of a point of reference for when last humans were there. But it's only good, carbon-14 is only good for about 22,000, 25,000 years. Okay? And then the detectability of that isotope in your sample is gone. Okay? So you cannot use carbon-14 to date things like dinosaur fossils. And dinosaurs, haven't been around for hundreds of millions of years, and therefore you can't use something that has a half-life so short. Okay? Instead, we can use things like argon and other isotopes that last maybe a billion years is their half-life, or maybe their half-life is a few 100 million years, something like uranium. But we have to choose something, if we're dating fossils, we have to choose something that occurs naturally in that organism. Argon is one of them. It occurs naturally in the organism's tissue. Uranium-235 does not occur naturally in organism's tissue, or for the most part it doesn't. Okay? So we're not going to use that. Okay? Now, there's lots of other things that you can do with isotopes. Cesium, strontium, cobalt, all these are used in cancer therapy. Okay? Phosphorus-32 is used to trace biological aspects. So we use phosphorus-32 to trace a lot of DNA. So this is how we figured out that DNA was the material for genes. This is how we figured out the exact shape of DNA, the bonding points of DNA, how DNA unzips and copies itself. Okay, and that really was clarified by using phosphorus-32. There's lots of other things that can be utilized. Some things very harmful, or can potentially be harmful. Maybe you're in a region where radon is important, so radon 222 or radon 220. These are isotopes that can be found in soil material, and so when they build houses and they build a basement, this material can be released into the atmosphere in the basement, okay, and has been known to cause lung cancer. So this is why a lot of people have radon tests done in their new home to figure out if that isotope is present or not. Okay. So there's lots of situations. Anyways, we're really interested in pretty much uranium. Plutonium is also of interest when it comes to energy. So how does it work? Okay, so there are three main radiation types, or three types of energy that's released when that material is decomposed. And the first one is an alpha radiation. Alpha radiation is by far the most serious. It can cause genetic mutations, but it's also probably the easiest to protect from. So most of alpha radiation can be just protected from layers of skin. So like, your epidermis, your outer layer, can protect you from alpha radiation. Beta radiation can also have serious effects, but you can protect yourself from this from layers of clothing, glass, aluminum, these kind of things. The least, I don't want to say the least harmful, but the least likely to affect you through mutations is gamma radiation. This is also the one that's most likely to penetrate you. Gamma radiation or electromagnetic radiation, it can go through several layers of lead, concrete. It goes easily through your body. But for the most part, it doesn't have too many adverse effects on your genes, on your genetics, and it doesn't really cause mutations. Okay? So we're really concerned with alpha radiation and potentially beta radiation. We know gamma radiation occurs, but it's not as big of a concern. All right, so how this works is you devise a mechanism, a nuclear fission, where the nuclei of an atom, in this case uranium, okay, is going to be split. It's going to be broken. Okay? And that creates what we call a nuclear chain reaction. So when you split a nuclei, okay, the neutrons are released. And they're released with enough force that they can hit other nearby nuclei and cause them to release more neutrons. Okay? So you get this nuclear chain reaction, things bumping into things. Okay? It's just like a 40 car pile up on a freeway. Okay? All it takes is one person to hit one person, and everybody's following so close, okay, that everyone crashes. Okay? And you get this big reaction, lots of energy being released. So here you can see, now this definitely depends on the concentration. There is a threshold concentration, just like a threshold of a multi-car pileup on a freeway. It's not going to happen if you got, one car that gets in a car wreck with another car and there's not any other cars on the freeway. Okay? It takes a lot of material to be in solution, to be in source for this to occur. You initiate excuse me, you initiate that first reaction, that first neutron to release. It's released, it breaks up this atom, and then those neutrons hit preceding atoms, nearby atoms, and release their neutrons. And this just continues, and as the neutrons are being released, the energy is being released. Now, you're going to have some fragments, some fission fragments. We'll talk about those. That's waste products that occur within these nuclear reactions. Now there are, again, like I said before, only certain kinds of atoms that this works with. Okay? One of those is uranium-235. Okay? Plutonium-239 can also be used, however, it's not as convenient as uranium-235. Plutonium-239 is great for like nuclear warheads, nuclear bombs, okay, but not that great for the construction of energy. Now, there's another thing, like I just said. You have what we call a critical mass that you have to meet. Okay? You have to have a certain amount of nuclear fuel in order for the chain reaction to occur. The critical mass cannot be too much, okay? Because if you have too tightly packed molecules, the energy won't be high enough. You won't get a big enough reaction. If you have too few, you will not the amount of travel time or amount of space the neutrons have to travel in solution is too great, and you won't get that pile up. You won't get that reaction by reaction, that chain reaction occurring. All right, so what does a nuclear reactor do? It permits a controlled chain reaction, a controlled nuclear reaction. Okay? So it's breaking a nuclei to cause that chain reaction, other for neutrons to be released, okay, and drive those other reactions. You must also have a moderator, and this is normally water. So this nuclear reaction occurs, energy is being released, you have to have some place for that energy to go. Most of the time that's in a water that occurs around what we call a fuel head or a fuel rod, okay, and the water absorbs that energy, and then that water can utilize that energy to spin a turbine. It can evaporate, and this is why you see nuclear reactions with a lot of steam coming off. It evaporates, that water evaporates off, okay, spins turbines, generates electricity. Okay. Graphite is sometimes used, okay, and then you can convert that graphite in energy from the graphite into water also and create that steam the same way. Okay. So basically the reactor or the way electricity is formed is very similar to fossil fuels. So you take coal and you're burning the coal to increase the temperature of water. That produces heat, that produces steam, that steam turns a turbine, generates electricity. Okay? Same thing with the nuclear fusion reactor, except for instead of burning fossil fuels, you're using a fuel cell, a nuclear fuel cell, and you're splitting atoms. You're breaking atoms down. Now, there are three common reactor types, which probably by far the most reactors, for sure in the United States, are pressurized water reactors, but worldwide they're pressurized water reactors, which means your fuel cell is in the center of water that has been pressurized in a capsule, and then the energy is released around that, which is then going to evaporate other water, which can then spin turbines. You can get boiling water. This occurs in a couple, and then you get heavy water where you're combining water with other material. Now, I know this only makes up 90% because there's another 10% out there which we call gas-cooled reactors. Now, gas-cooled reactors are very, how should I say this, controversial, because you can take gas-cooled reactors and utilize it to not only produce electricity, but also use the byproducts sometimes to produce nuclear weapons. Okay, so you kind of get this twofold aspect. Most gas-cooled reactors are heavily regulated and are a concern in the world. All right, so nuclear fuel cycles, again, most of this comes with the mining of uranium. Okay? Australia, Russia, South Africa, Kazakhstan, Canada, United States, all these places mine uranium ore, okay? And then they process that uranium ore. They mill it, they crush it, and they treat it with solvents to make concentrated uranium. The problem with concentrated uranium, well, it's radioactive, but there's other issues with it. Okay, we call it yellow cake. So you get this milling process. It's this yellow material, okay, and that contains about 70 to 90% uranium oxide. Depends on the process. It depends on the milling process and the solvent used and the beginning uranium ore. What what grade that uranium ore is, how much uranium oxide to be formed. Okay? But from there, that's not the only step. Uranium oxide is not really fusionable. Okay? So only about, when you take uranium ore out of the ground, it's only about 0.7% is uranium-235. The rest is normal isotopic phase of uranium at 238. Okay? So right there, every chunk of uranium you're bringing out, you're digging out of the planet, less than 1% is usable for nuclear fuel cycles. Okay? That's problematic. Apart from that, you also have to enrich the uranium-235, so you have to get to a 3% concentration in order for nuclear reactors to work. Now, I say most nuclear reactors, some work under the 3% threshold, okay? But most of the nuclear reactors, of the 450, I'd say 90% that occur on the planet have that 3% threshold for uranium-235. Okay, how do you separate this? You take it, you put it in solution, and you centrifuge it. And you centrifuge it. Remember, 238 is going to have a different mass than 235. So you can take that, centrifuge it. It's going to separate the two based on mass. You can pull the fusionable 235 off, and you can discard the non-fusionable part, 238. Okay. Then that material is ground into a powder, right? And pelletized. So it's centrifuged even more to form a pellet. Once that pellet has been formed, it's sealed into metal rods, which we call fuel rods. Okay, and then it can be placed into a reactor. Depending on the chamber, will depend on what kind of reactor it is. Is it a pressurized water reactor? Is it a boiling water reactor? What type of reactor are we dealing with? But that fuel rod itself is really no different depending on the reactor, okay? Or not much different, I should say. Now, as the fusion occurs, so as you break the nuclei of some uranium-235, over time, the concentration of U-235 will decrease, okay? Because it's, you're breaking neutrons, okay? And you eventually change U-35 into a different element because the protons will also leave. Okay? The half-life of a fuel cell or fuel rod is about 3 years. So you got about 3 years of operation, and then that fuel cell has no real function in that nuclear plant. Okay? So the radioactive material is too little to drive the chain reaction. Okay? So then what you have to do is you have to insert a new fuel rod. Okay? Now here's the problem. Okay? Spent fuel rods are still highly radioactive. Okay? It still contains roughly 1% uranium-235, but also now it contains about 1% plutonium. Okay? Now, this is the kicker with it when it comes to nuclear fuel cycles. Most of these fuel rods are dealt with as waste. Okay? We're going to watch a little video about what's done with the waste or what's not done with the waste. But most spent fuel rods, actually, you have the capability of taking that spent fuel rod and recycling it. You can remove the 1% plutonium, and you can add new uranium-235 to the fuel rod and reuse it. Okay? Now, there are lots of countries that do this. Okay? But if you remember back from the figure I showed you, the United States has the majority of the nuclear plants in operation, and we do not recycle our fuel rods at all. There's not a single plant in the United States to date that recycles fuel rods. So therefore, we create a massive amount of radioactive waste, and we have to put it somewhere. Okay, so every 3 years of operation, you're getting, a fuel rod, which is not a small thing, worth of nuclear waste, and you have to get rid of it. Oh. I think I'll show you the video next time. Okay, so this is going to go into, I'm sorry about that, but this is going to go into or flow into issues with nuclear energy. Okay, so to this point, really it's fairly productive, I guess you could say. Creates quite a bit of energy, and there is really no atmospheric waste, because the material that comes off the big, you know, cooling vats, that's just water vapor. Okay? There's no actual toxic material. It's not smoke or anything like that. It's just water vapor that's coming off. The real waste product comes in the spent fuel rods or the spent nuclear rods. Okay, those have to be dealt with. Okay, that's going to proceed into our next topic, where I talk about the issues of nuclear energy. Okay.